Hello everyone, I am Benjamin Ripsch, Research Associate at Fraunhofer IGP, and I'm here today to talk with you about bolts. In steel structures, bolted connections are everywhere, as they are a good way to establish connections between different structural members and components. However, bolts coming loose on their own can be a problem. And in the last few years, there have repeatedly been reports of bolted connections on boat landings of offshore wind turbines to do so. As loose bolts on boat landings are expensive to exchange and as they can be a life-threatening danger to offshore personnel, we wanted to find out how this could happen. Therefore, we took a look at the assembly of bolted joints under the influence of water, in particular at the influence of water on bolt preload and slip factor. First, we're going to take a look at what kind of bolted connections have actually been affected by self-loosening and how they work. Then I'm going to give you a short overview about self-loosening, its reasons and countermeasures, before we look at the actual investigations. With boat landings of offshore wind turbines, assembly and tightening of bolts on site is sometimes necessary. Some of these bolts are located in the splash zone or even underwater, as you can see on the right. Now, it is interesting that especially bolts tightened under the influence of water appear to be prone to self-loosening. So, what kind of influence could water have on the strength of bolted connections? You're going to know at the end of the presentation, but first let's have a more detailed look at the bolted connections that have come loose. Joints in question are slip-resistant connections designed according to Eurocode 3 and executed according to EN 1092. High-strength structural bolting assemblies of class 10.9 with nominal thread diameters of about M27 were used. They were initially tightened by torque control and retightened after about 500 hours. The structural steel flange plates were coated by thermal spray with a zinc aluminum coating. For a better understanding, let's have a quick look at bolted connections according to Eurocode 3. Within the standard, bolted connections are categorized according to load direction and the level of preload applied. So there are shear and tension connections as well as preloaded and so-called non-preloaded connections. Slip-resistant connections are preloaded shear connections, which you might also know as friction connections or friction joints. For these connections to work properly, you have to apply a minimum preloading force, which depends on the size of your bolting assemblies. Also, you have to consider the slip factor, which depends on the surface treatment of your faying surfaces. Now, knowing what kind of bolted connections we are looking at, let's see what causes bolted connections to come loose and what kind of preventive measures we can take to keep them stay strong. Self-loosening basically means that our bolted connections suffer a loss of preload. This can happen either by rotational self-loosening or by slackening. We're going to take a look at rotational self-loosening first. Rotational self-loosening can either be partial or total, and there are multiple reasons for rotational self-loosening to happen. Most obvious, a loosening torque could be applied. Also, axial and especially shear loading can lead to slip between the joint components, which can ultimately result in bolts turning loose. This can be prevented by designing and executing bolted joints as slip-resistant connections or the use of bolt locking devices and methods. As our boat landing bolts are exposed to cyclic loading in multiple directions, designing them as slip-resistant connections was certainly right. But considering the presence of water during assembly, the two key aspects of design might actually be altered when executing or respectively assembling and tightening the connections on site. The maintenance of the as-delivered lubrication is crucial for high-strength structural bolting assemblies for achieving the nominal minimum bolt preload with the tightening methods listed in EN 1092. Typically, HV nuts are lubricated with molybdenum disulfide, which is actually well known to reduce its friction properties in contact with water. Also, the slip factor might be influenced by the presence of water in between faying surfaces as well. We did a lot of tests to see how strong the influence of water on both of these key design aspects is, and I'm going to show you in a minute. But first, let's look at other ways to prevent self-loosening. Another way to prevent rotational self-loosening is to use so-called wedge lock washers. Having a European technical approval, wedge lock washers can be used with high-strength structural bolting assemblies used according to Eurocode 3. In order for them to work, a minimum bolt preload specified by the manufacturer must also be applied. Another reason for self-loosening is slackening. Slackening can be caused by creep of the connection components or by settlement. Preventive measures are the application of a sufficient amount of bolt preload and to consider settlement effects. The level of bolt preload applied is highly dependent on the tightening method chosen. With torque-controlled tightening, a bolt preload is typically the lowest and friction dependence is high. This is the way our boat landing bolts have been tightened. EN1092 also allows angle-controlled tightening with bolt preload significantly higher and above yield strength of the bolts. A tightening method not listed in EN1092 is yield-controlled tightening, where special tightening equipment is used to stop the tightening process when the bolts start to go into plastic deformation. With angle-controlled tightening and yield-controlled tightening, friction dependence is lower than with torque-controlled tightening. A different way to achieve higher bolt preloads, especially with torque-controlled tightening, is the use of so-called Z-washers, which make axial tightening without the need for a reaction arm possible. They can be used in Z with special backup washers, which prevent bolt rotation while tightening without a backup wrench. So let's finally take a look at the investigations. We did a lot of underwater tightening and settlement tests, and we also developed a setup to perform regular slip factor tests underwater. For our tightening and settlement tests, we instrumented HV bolts of size M27 and M36 by the application of strain gauges in the middle of the bolt to measure bolt preload. We put them in a box full of salt water, assembled two flange plates with a thickness of 30 mm each, and finally tightened the connection underwater. We used regular plain chamfered washers as well as the other washer systems mentioned earlier and the tightening methods listed below. After tightening, we measured bolt preload for about 72 hours. Doing so, we could see the initial bolt preload applied with the different tightening methods, and we could also detect the according preload losses. For a conservative view on bolt preload over the lifetime of the bolted connections, we extrapolated preload losses to a theoretical lifetime of offshore wind turbines of 25 years. For underwater slip factor testing, we basically put our regular slip factor test setup inside a saltwater tank. Slip factor test specimen consists of two center plates and two cover plates held together by 4 bolt assemblies. During testing, the center plates are mounted in the testing machine and torn apart vertically to determine the coefficient of friction of the plate surfaces. Our test procedure was based on the specifications given in Annex G of EN1092. For reference, we determined the slip factor under regular conditions first, before we did all the testing underwater. To determine a so-called slip load, 4 slip factor tests have to be performed. The slip load determined gets then tested under static load within the creep tests. If displacement crosses the defined threshold in a certain amount of time, reduced loads have to be statically tested during extended creep tests until the acceptance criteria are met and the final slip factor and surface class can be defined. Let's have a look at the results. You can find all the single graphs and diagrams in the actual paper, so what I'm going to do right now is to give you a short summary of what we found out. As you already know, lubrication properties of molybdenum disulfide degrade in contact with water, and for bolts tightened by torque, this means that the nominal minimum bolt preload could not be reached. The implication for our boat landing bolts is that even though they might have been designed as slip-resistant connections, they presumably have not been executed as such. Under cyclic loading, self-loosening might thereby be possible. We could see preload losses in a range of about 10 to 20% for all connection setups tested, which is in line with preload loss examinations performed under regular conditions for these kind of zinc aluminum coatings. Again, for bolts tightened by torque, this means that the initial bolt preload does not reach a level that is demanded by design, and that this preload, which is already too low, is reduced even further during the lifetime of the bolted connections. The slip factor tests confirmed surface class B for the zinc aluminum coating under both testing conditions. However, slip behavior of the connections tested underwater looked different from the connections tested under regular conditions. While specimen tested under regular conditions continuously slipped until they came to a hold slowly, specimen tested underwater slipped continuously until they lost hold abruptly. Bolts tightened with alternative tightening methods compared to torque-controlled tightening reached satisfactory levels of bolt preload, meaning above design preload level, even with degraded lubrication. Still, degraded lubrication is not desirable with angle or yield-controlled tightening either. In case friction gets too high, there is a danger of bolts turning while being tightened if not secured properly, which would lead to misleading tightening results and preload slower than expected. In case friction is even higher, angle-controlled tightening might lead to bolt overload due to high torsional bolt stresses. With yield-controlled tightening, friction this high could lead to the tightening process being stopped early and before minimum bolt preload is reached. We've actually seen all of these things happen with bolt size M16. So after all, the verification of friction properties is still advisable, and in this case, the alternative tightening methods examined are not the easy way out. And although using alternative washer systems can be a good idea, they also depend on maintenance of the as-delivered lubrication of the bolt assemblies, which cannot be guaranteed for when in contact with water. So in future research, we might have a look at alternative lubricants. Also, hydraulic bolt tensioning can be used as another way to tighten bolts underwater, as it is common practice in offshore oil and gas industries. Finally, slip factor testing under the influence of water might be advisable for all kinds of surfaces used in slip-resistant connections assembled underwater, as each material or surface preparation might behave differently. So what we've learned is that assembly and tightening of bolts under the influence of water can lead to serious problems if not handled properly, and that it is the as-delivered lubrication of high-strength structural bolting assemblies that seems to play a critical role here. If you have any questions concerning the topic, feel free to ask or contact me later. That concludes my presentation of a research project that was done in collaboration with multiple partners from the bolting industry. Thanks again for the support.